Okay. Uh, you can see my screen, right? Okay. Right. So this is the place that we stopped in last time. So we have completed kind of stuff. So if I go to the previous slide, actually there are 27 kind of slide as well, but I'll give you a quick summarize, right? So actually we talk about the Hadoop platform, and it's a platform that's used to store and process very large amount of data across many computers, right? Not a kind of a single computer. So because it's become kind of an important kind of thing, because in modern organization it produce huge amount of data, right? So the one computer can be alone cannot store or process it kind of efficiently, right? So because of that, but bottleneck, the Hadoop platform is introduced, right? So the main idea of the Hadoop is kind of a distribute computing. Okay, so instead of using one powerful machine, Hadoop uses many ordinary machines work together, right? This makes a kind of a system is scalable and also kind of fault tolerant. And because even if one machine fails, the whole system can be continuing working, right? So then we talk about the HDFS, MapReduce, and the other one is kind of ecosystem, right? So to kind of do the kind of the ecosystem or the applications, how to we will talk about the how to do the applications on the top of the Hadoop, right? So I will give the context for here, and I think we don't I I plan to do a kind of the Hive kind of stuff, but the thing is we don't have get the time, right? um so then the other thing is actually, as we discuss about the HDFS, right? So we discussed a kind of a one lecture as well, right? So HDFS, it stand for Hadoop Distributed File System. Okay, so the it store very large file by breaking them into blocks and spreading those blocks across different machines, right? So then it also keep multiple copies of each blocks, and usually kind of default number is 3, right? So then also data is protected if machines or display, right? So then in the HDFS there's a name node, which manages metadata, and where the each block is stored, but it does not store the actual data, right? So then if you go talk about the data nodes, it's the place that we can say the actual data is stored, right? And then we can say that the name node is kind of a catalog, while data nodes are like the kind of shelf that holding the real books, right? The second important part of Hadoop is kind of MapReduce, right? So in the MapReduce, it's used to process the data stored in HDFS. Okay, so it works in three main stages, right? Kind of mapping part, then shuffling part, as well as reducing part, right? So in the map stage, actually data is converted into a kind of key value pair, and in the shuffle stage, similar keys are grouped together. The reduce stage, the group data is kind of processed and produce the final result, right? So we talk about two examples in the slide actually, the word count example as well as the kind of the temperature and the city example, right? So for simply the word count one, what will happen is the mapper read the lines of text, and you know and the outputs for each word with the kind of value one, right? It shuffle the same word together, and then finally the reducer add the values for given total number of count for each word, right? So that's the kind of an important concept as well. And then the other thing is actually, so we talk about the third part, they had to also have an ecosystem, right? So they need look kind of the big and Latin. kind of stuff, right? So that's where we actually stop. And today let's focus on this one, right? So the building the kind of applications on the top of the Hadoop, right? So there are five tools that we are going to talk about today. One thing is Peak, another thing is Hive, then this is Jackal and Zookeeper and HBase, right? So if you talk about the Peak, and I think it's a kind of a data flow scripting, right? So so for people kind of thinking load kind of data, then filter, group, and then join kind of stuff. So that one we can use it, right? So the Hive is kind of it's SQL and Hadoop, right? So the people, you know, that means the analyticals stuff, the analytics. If they want to know about the Java in depth to kind of write a kind of a Java code for the analytical stuff, that's not good, right? So the thing is actually analytics who already speak about SQL and who do not want to write Java code, we can use Hive, right? So Jackal means actually JSON query language, right? The for the people who work in with semi-structured nested data like JSON documents, they can use it, right? Showkeeper is kind of a coordinate service. So that means quietly it's used by other tools to agree on the kind of configurations, leadership, and steps, right? So then HBase means it's a column type disto, right? Column oriented disto. So that means, for the application that need kind of fast random read write access for the huge table, so then it can be used, right? So the so this is the one actually um uh, uh, kind of tools that we are going to talk about. The reason behind that is you know, um, in everywhere in the software, the kind of the Linux kind of become friendly with the shells, then the containers kind of stuff, right? So then the SQL database also become friendly with the object-oriented mappings, the BI tools kind of stuff. Okay, so then the the main important part is the ecosystem story of the Hadoop is the same, right? So the core was Java MapReduce, but this kind of stuff layers about made it for usable for many roles, right? So that's why the Hadoop is become made many much more popular because on top of the Java and the MapReduce kind of stuff, it we can the analytics or any kind of role that they play, so they can use this on top of the Hadoop. Okay, so this is the kind of pig Latin, right? So pig Latin is the language. Okay, so then that means you know the high level kind of scripting language that used for describing data flows, right? So if you write a statement like load, group, filter, join, for each kind of stuff, this kind of statement is kind of much closer to this the big Latin language, right? So then it is originally actually developed by Yahoo, and it's focusing on more analyzing the large set of data, right? So again, it has two components. The pig is the language itself and the runtime environment, right? Where the pig Latin programs are executed, right? So the reason behind the stuff is, spending less time writing mappers and reduce. Okay, so it is kind of a stuff, that raises the kind of abstraction level. So instead of uh, writing dozens of Java files for each map and reducer, you can write in a kind of a few big Latin lines, right? So that means, instead of explicitly thinking about the map and then reduce kind of stuff, so you think how to load it, then transform it and group it and kind of store. Okay, so this is how the data engineers is kind of naturally describe their pipelines, right? So that's why the pig was designed to handle any kind of data, and it's structured, semi-structured, even messy data, you can use it, right? So you can use kind of define schemas if you want, and but you don't um, you don't have to, right? So if you want, you don't have to, do kind of much complex stuff, right? So the flexibility is kind of useful to kind of exploitative work. That's the kind of stuff the pig and pig Latin will do. So actually, I'm not going to deep dive into kind of these kind of stuff. That will be kind of another lecture, right? So in your scope, so what you have to do is, okay, you have to know these are the things that you have to do on. So you can you in the YouTube, there are tutorials, right? So in that one, if you want to kind of get a practical scenario, you can do it, right? So because if you are doing the practical scenario, we have to do big hive and kind of this kind of stuff as well, right? So that's now there are much to complete from my side as well. So that's why I skip this the practical scenarios. Otherwise, I plan to do this high one practical, but so there are another things that we need to complete. So it's better to know these kind of ecosystem names and what's the use for that one, right? So then this is the Hive one, right? So Hive also is scale on top of Hadoop, but it's built at Facebook, right? So then actually, there are three things that I will give you, right? So it's familiar to SQL developers. So that means any person who is fluent in SQL, then they can leverage on Hadoop, right? So they do not need to learn Java or MapReduce, any new language, right? So then the other one is HQL. HQL means the high query language, right? So it's look familiar to standard SQL, but you can write select from where and those kind of similar familiar pieces also including here. So other thing is kind of automatic translation. Okay, that means kind of the SQL become MapReduce, right? So that means the Hive service break each SQL statement into MapReduce jobs and then execute them across the cluster. Okay, so the user never sees that kind of translation, right? So that's why this Hive is much more popular. So think about that in the HDFS. Yeah, if you want to kind of do kind of analytical or processing stuff, kind of aggregation stuff with the use of data that is stored inside the HDFS. So typically, what we have to do is we have to write Java for kind of map and reduce. So instead of learning the code base and kind of Java language, the analytics, people who are doing analytics, they do not want to do that. So even if you are doing kind of analytical stuff, the learning the skill is kind of much more important, right? So even now in the modern industry also, you know the people who are doing chemistry or physics or kind of stuff, if they are in the kind of I know that there's some of my friends, they are actually following the chemistry path, right? But in the when they apply to kind of the foreign universities, and when they started to their PhD kind of academic stuff, first thing is actually there is a kind of they say that there is a kind of a lecture series for SQL. Okay, now right now actually they have kind of lecture series about AI as well. Okay, now that's why the foreign university, you know um, they are changing their syllabus and kind of stuff according to the technology changes, right? So that's why I am telling that the people who are doing kind of analytical stuff, now they have a kind of knowledge about SQL, but they don't have knowledge about Java, right? So the Hadoop is kind of a stuff that on the top of the Java, they build a kind of frameworks like Hive. So because it's pretty much easy for use who are not kind of familiar with Java, right? So that's why after Hive, every business analytics and every BI developer, every database administrator could work with the Hadoop, that they have skills, right? So then this is why the Hive was kind of a single kind of a bigger reason that Hadoop went from the kind of you know very much popular, right? So then the other thing is actually this Hive. It shows how an ecosystem kind of can be democratic, a powerful technology, right? And the the interface is much more familiar since it's a kind of a SQL interface. And yeah, that's the thing actually. We need to know about the Hive. So, but again, I would like to say there are, if we are talking about Hive, there is another lecture series to do, right? But I will kind of sound knowledge, right? So then the other thing is actually Jackal, right? So it's a kind of a query language for JSON. It's developed by IBM, right? So the JSON first query language, and so it's a primary that query language for JavaScript object notation, right? That means JSON, and it was developed by IBM, and it can be used handle nested and the kind of irregular records. That's kind of relation is schema would struggle with, right? So it's allow processing both structured and non-traditional data, and it's operates on HDFS. So then in the Jekyll, actually, you can use select, join, group, filtered data, and that is stored inside HDFS, right? So it's just like Hive, but it's a JSON shape data model is instead of one tabular one. So you can use in here the select, join, stored in the HDFS as well. So the other thing is actually the blended influences, right? That means it's syntax drawn from a kind of SQL, XQuery, and Peak, right? So it has kind of a slightly unusual feel, right? So then the more functional than SQL, but more nested than the Peak. Okay, that's why it's a kind of blended kind of influence. So it's a kind of existing in the ecosystem because it's important, right? So it reminds us kind of a, let's say, a real world data is often messy and nested, right? So you know that. So right now, we are using kind of a JSONs, right? So if you are going talking about the IoT input stuff like that, so we are using kind of a JSON, right? So then there are another things kind of log records from the microservices and document stores as well. So now that's why the real world the data is kind of often messy, right? So then the Hadoop ecosystem need a kind of a language that can query such data without forcing into a kind of a flat tabular shape first. Okay, so that's the thing actually you need to know about the Jaguar one. And the other thing is kind of a zookeeper, right? It's a it's all actually a different kind of problem than Hive peak, right? It's not a kind of a query, no transforming data. Actually, it's kind of a coordination of the distributed processes. Okay, so the Zookeeper actually it provides a kind of a highly reliable services for distributed coordinations. Okay, so especially it offers a kind of a hierarchical key value store, kind of a distributed file system that small bit of metadata, right? And kind of a synchronization services, right? That means the processors can look the resources. So if we wait for another events, then uh, we have synchronizes kind of stuff, right? Guys, can you give me 1 second? Okay, so yeah, so then so that's the kind of stuff actually Showkeeper does. Okay, so then there are some important points that we can talk about. It's an open source server which is highly reliable distributed coordination of the cloud applications, right? So so once the system is distributed, actually, it's hard coordination problem kind of stuff is multiple, right? So that means how do the nodes agree on which node is leader, then kind of stuff, right? So the other thing is how do they discover each other when new ones joins to the cluster. Then other thing is how they handle the situation where two nodes both are kind of thinking kind of they are kind of same stuff of doing. Okay, so that's the kind of a main problem that Zookeeper addressed on, right? So without like a tool like a Zookeeper, every distributed system would have to solve the problems from the scratch, right? So and they are very hard. Okay, so then the Sucubis actually provides the battle on tested and common solution that the kind of other system of built up of. Okay, so then for example, the HDFS and MapReduce are thinking about the storing and processing of data, and Showkeep is the thing that actually help of distributed components agree on that one and actually kind of coordinating stuff. You know, the processing and the storing data as well as the coordination between those systems, they are both are essential, right? And but actually they are kind of like answer very different questions. Okay, so that's why I think some of the people they underestimate the Zookeeper because it's kind of an invisible one, right? But the actually Zookeeper also kind of playing an important role in here. So that's why the other thing is actually it says that the maintain common object need in large clusters and kind of the application leverage on the services coordinated distribution system also across large clusters, right? So these are the kind of points that need to talk about the Zookeeper stuff. Okay, so okay, and okay, so in a Kafka kind of stuff, the Zookeeper actually it's historically tracked the which brokers were live and kind of which were the leaders of the partitions kind of stuff, right? So without coordination, again, the producers and the consumer would not know about each other, how send and read messages kind of stuff, right? So we will talk about the Kafka as well, but inside that one, the Zookeeper also there, right? Um, so now the other component is kind of HBase. Okay, so this is a column oriented on HDFS. Okay, so HBase is a kind of a column oriented database management system that runs on HDFS, right? So HBase actually it's a uh, running on the top of the HDFS. So unlike relational system, it doesn't support structured query language or SQL, right? So then actually the other thing is tables, rows, and columns. So HBase system has set of tables, and each base table it contains rows and column, much like a relational table, but inside this row, the columns are grouped into column families, and they can be sparse actually, right? So different rows can have different column kind of set, right? That's why it's a known as column oriented on HDFS. Okay, so then definitely it's the primary key is required, and every table must have kind of a primary key, and the all access attempt to HDS HBase table must go with the through these primary keys, right? So the other thing is actually a column, it's equal to an attribute, right? For example, if you are talking about the log record table, so you need to have kind of a column like timestamp, severity, message. kind of stuff, right? So each column represent one attribute of the log event. And the the plain HDFS plus MapReduce is a great for back scanning, but so let's say like this, right? So fetch a one row by its key in a kind of millions of record, right? So if we want to fetch one row by its key on a few millions of record, we have kind of a query cost, right? But the HBase fills that gap. So it uses a kind of a HDFS as a storage layer underneath, but the adds and kind of a indexing, a kind of a server layer actually on top of that one. That's why the HBase is exist on. So that's the thing actually we need to talk about the HBase. Again, I would like to say, if we are deep dive into this kind of example, so then we have to do another kind of lecture series, right? So I am talking about the components on the kind of a kind of a sound knowledge, right? So then I will just go through this one, and I want to say why this kind of technologies uses, because when we are having the kind of Hadoop platform, so when they are built on that one, so they face different kind of problems, right? For that different kind of problems, they introduce different kind of tools for address each type of problems. Okay, so that's why, for example, HBase we are talking about. If you want a kind of a row in a kind of a millions of record, so then there is a kind of a query cost. So for fill of that gap, actually HDFS kind of HBase is built on the top of HDFS. So okay, that's why actually HBase also there. So then let's talk about the data formats for Hadoop. Okay, so okay, and so now the Hadoop is kind of process huge volume of data, and HDFS is built for large scale of storage, right? But the performance shape, it's not just by the cluster or science or kind of a programming model. So it's heavily influence how the data physically stored in a disk, right? So that's why these kind of ideas we used in that one. So one thing is process huge volume of data to MapReduce. Then that means the whole ecosystem is designed around this one, right? So whatever the format we choose to, has to be kind of efficient in large scale, right? Not just a kind of a small convenient amount of scale, right? That's why the Hadoop ecosystem is designed on process large volume of data and distributed through the MapReduce programming model. And the other one is HDFS, right? So we talk about this one. It's designed for large scale of data, and where the data, these three properties maps together, right? The scalable, flexible, and performant. Okay, so then the format you store in the data, it determines how the HDFS potentially you can actually rely on, right? So the other one is master slave architecture. So we talk about this one as well. The Hadoop works on master slave architecture and store data in HDFS kind of stuff. Okay, and okay, so this also we talk about the name node and the data node, and I just include you because when you are reading from the beginning of the slide, so then again you will remind how this working, right? So the name node and data node, we talk about this one deeply, and we talk about why the HDFS blocks are very large. The block size is kind of deliberate on trade-off between seek time and transfer time, right? So then the reason actually the understanding, it helps you to understand how the Hadoop and why Hadoop is flavor for huge files over many small files, right? So the reading from a discuss to cost component, right? So one component is seek time. Okay, the time that discom takes to find the start of the data, typically it's kind of 5 to 10 milliseconds, I think, right? So the other thing is transfer time. Transfer time means actually the time actually read the bytes once you have to find it. Okay, it depends on the disk speed, typically, tens to 100 of megabyte per second, I think. Yeah, it's kind of 10 to 5, I think. Yeah. So for example, if a small block, say kind of a 1 MB, the seek time is kind of dominates, right? So you spend almost as much time to find the block as read enough, right? So if a block size is kind of 1 to 8 MB, the transfer time is dominates, right? So that's why I say that the seek is the one time cost, but and as well as the long SQL read is highly efficient. Okay, so that's why this kind of steps we I introduce in here. And the minimize the seek cost, right? So that means the large blocks can aim on the minimize the cost of search, right? If a block is large enough, transferring from this takes longer than the seeking time of Vista, right? So then the other thing is the replication of reliability. That means the block fit well with the replication for fault tolerance and availability. That's the reason why we are kind of doing replication, and each block is replicated across several small separate machines. Okay, so and the other thing is actually any kind of data. So actually Hadoop store information on any format, right? Structured, semi-structured, and unstructured. Okay, so the block size is actually not just a kind of a Hadoop kind of a kind of a let's say kind of a quirk, right? So in kind of the large system unit you can operate it on, and it's better to uh, have a kind of a principle applies on database such as file system, even network design, the large packet of kind of a same trade-off stuff. Okay, and yeah, so I talk about this kind of concept actually inside the HDFS lecture. And okay, this is the part that we are talking about the file formats, right? So there is no kind of a default file format actually. It's a right choice on depend on use cases, right? So we are the people, we are the you know um person who need to uh, pick the right file format, right? So it depends on how fast you can append to new data, the optimize for write time. So then it should open on read time, how fast that you can scan or query the data. Then the file divisibility, that means the can framework is split file into independent chunks of parallel processing. Compressed file formats are not splittable, right? So it kills actually the parallelism. Then the other thing is adaptive scheme. That means can the file structure change over time as you application ignores, right? That means, for example, adding new fields, renaming fields, kind of stuff, right? The other thing is compression support. That means that does the file, um, does the format compress well, right? That means that does it support block level compression, or individual chunks can be decompressed that means decompressed individually, right? So those kind of stuff we need to think about, right? So that means the each stage of data processing may need a kind of different format to be efficient. So the goal is to choose the format that maximize the advantages and minimize the inconvenience. Okay, that's why we are telling that based on these kind of facts, we need to choose the kind of the right file format. Okay, so so now these are the most common file formats. So there are 6 common file formats in the Hadoop ecosystem that I have included in here. The one is text slash CSV. Other one is sequence files, the binary key value pairs. Other one is Avro, it's row based with schema. Other one is Parquet, right? So Sama is pronounced as Spark, and some are pronounced as Parquet. Sound, I think T is silent. I think the correct word is Spark, I think. So other one is RC file, and then other one is ORC. Okay, optimized row column oriented one, and this is a row column oriented file, right? So the text file actually it's a human readable and it's easy to produce kind of stuff and most not the most efficient at the scale, but it's a kind of a most human readable one. The CSV, know that one. The sequence file actually it's a binary key value pair in the Hadoop native container, right? So it's more efficient than the text, but it's not human readable since it's a kind of a binary format, right? Other one is Avro. Avro means it's row-based binary format, kind of with the schema embedded such as JSON inside the file, right? So then the path means actually it's a column based column oriented binary format, and it's excellent in read, right? Because it's in a kind of a column based. And then the record column file means it's a hybrid format. It's pretty much older, but the row groups contain in column layouts kind of stuff. And the other one is actually optimized row column oriented one, and actually then an evaluation of the the kind of record column one as well. So that means it's a kind of a evaluation from the record column oriented file, right? The ORC one. So let's move to the text and CSV, right? Okay. So these are plain text and the most basic and the common readable format. You know that, right? So it's a kind of a basic and it can be read or written in any program language. It's commonly delimited by comma or tab, right? So one of the most common format, but both outside within the Hadoop ecosystem, right? So it's simple and no schema, no header needed. To the CSC, it can have header row, right? But no special tooling kind of stuff, right? There are quotients as well. So the quotient is kind of the waste space, right? The numerically stored as also test string, and it takes more bytes than the binary equivalent, right? So for example, if we take 1 to 10 kind of stuff, it take 10 bytes as a text, but only 4 bytes as a 32-bit integer, right? So that's why it's a kind of the consume more space when numeric values are stored as string. The other thing is difficult to represent the binary data. So it's difficult to represent on binary data such as image, and you cannot meaningfully store in a kind of a image inside the CSV, right? That's the thing actually we face kind of a cautions there. And the other thing is it does not support block compression, right? So compressing CSV in Hadoop can be have a high cost in read cost, right? So then that's why actually you know, it's recommended only for extracting data from Hadoop or doing kind of a massive load from the file, right? So, if we are talking kind of imagine that 10 billions of row scale tables in CSV, that if you want to query that you wants to only the total amount, the column still has to read from every byte of every row from the disk and just find the right column on each line kind of stuff, right? So that's why actually if we are kind of using kind of a Parquet file kind of stuff, it's I think kind of 50 plus improvement can be done by that one, right? So that's why we are not to recommend using kind of text or CSV format. So the other thing is actually the sequence file, right? So sequence files on Hadoop kind of stuff. It's a binary format that is storing key value pairs, and it is efficient and then text, but not a kind of a human readable one. So it's stored data inside in the binary and no text. So you cannot get the file or read it, or kind of you need to Hadoop tool to inspect that one, right? So then the key value pair is in a kind of a binary container. That means each record is a kind of a key value tuple, right? So it's both serialized and compiled in a kind of a binary format. So actually, this matches a kind of a Hadoop key value program very naturally, right? So that's why it's more efficient than the text file. And the other thing is compression. So it accepts the compression, but it does not store the metadata, right? So that means the SQL file, support record level as well as block level compression, but it does not store rich schema. So the only schema evaluation option is appending on a new field, that at the end of the value, right? So the other thing is actually best for intermediate data, typically used to store intermediate data in the input output might reduce process, right? So it's recommend for this purpose. And the whole program model, built on key value, right? So that's why, again, I would like to say the key value oriented file content fits naturally. So then the SQL file is a kind of a format that you can reach from where you want to, efficiency or over reliability, readability. And but if you do not need a kind of a rich feature of kind of stuff, you need to use Avro kind of a target one. So in the modern pipeline, it's using less often than they used to do, right? Mostly they are using kind of Packet or every file format, and and it take largely taken in place, right? So this is let's talk about Avro data files, right? It's a raw based storage format with the kind of a schema traveling along the data, right? That means actually it's a one of the more important format. Okay, so the central idea is kind of simple, but it's powerful. And there are four features actually. So one feature is kind of row based storage, right? That means each record is stored as a kind of a complete row, like just like CSC, but it compact in binary format. Okay, so that's the difference between CSC and Avro. So it's a compact in the binary format. So other thing is schema embedded as a JSON. Okay, so that means each Avro file include schema definition written in JSON right in the file, right? So the schema describe every field, kind of let's say name and type, and each file includes the schema definition in JSON, and so anyone with the file knows how to read it without external coordination, right? So the other thing is compression and divisibility. That means the Avro support block level compressions. That means the file remaining kind of exploitable on parallel reading. So allow block compression in additional to divisibility, right? That means making a good choice in mood in Hadoop scenarios. It's a good in actually Hadoop distributed in parallel processing models. So when Arrow is actually it's a kind of a good choice when the data is schema in only in over time, right? So that means it support well-defined rules for well involving kind of schema over time. That means adding the optional fields, then deprecating fields, providing default values for missing fields. That kind of stuff Arrow is pretty much supporting. So kind of evaluation is kind of what that makes Avro practical is long life data pipelines, right? That's why Avro mostly data pipeline they use it because this feature. When the schema may change, then it's a kind of a good choice, right? So then real in the real system, we all know that the fields adding the optional fields appear, structure is kind of stuff, right? A format that hands that changes gracefully is much easier to operate over years than a kind of a one assume that the world standard is. Actually, that's the thing. Um, we need to focus on why the Avro is oftenly described as the general purpose of data. Okay, so that means it's a good choice when the data schema can evolve over time. So yeah, so that's the uh, things that you need to know about the Avro data files. And these are the things that the Avro is general purpose on peak, right? So again, it's efficient in binary encoding. It's long-term storage, so ideal for long-term storage because it can read and write from many languages, Java, SQL, and others. And schema embedded, that means schema metadata can be embedded in a file to ensure it will all is readable, that kind of stuff. And the Avro is actually considered as the best choice for general purposes on had storage on Hadoop. So these are the things actually we need to talk about Avro. And this is the kind of call packet, right? So actually this is an important one. It's a column-based binary storage format, right? It can be whole nested data structures, and the column-oriented one is a nested support, right? That means it's a column-based binary storage format that can store nested data structures, right? So then the other thing is actually it's efficient in um, IO fits. That means when columns are specified. So the reason behind that is if your query read three columns out of 50, definitely Parquet reads only those three columns from the disk, right? Not the kind of a row based one. So if you want a row based one, so you would read all the 50 columns that for every row, right? So you have to just find it what's the row based format as well as column oriented format in the databases. Then it will understand you how this efficient in IO, right? So then it's built on a kind Cloudera and Twitter, right? So it's developed by Twitter, and it's supported in Spark, MapReduce, Hive, and each and every component, right? So then actually this is inspired by Google Dreaming. So that means it's a kind of a advanced optimization from the Google. There's a paper, right? So they need reduce the storage and improve the performance as well. So most analytical queries do two things, right? One thing is actually they touch the small subset of columns and they perform aggregations and filters. Okay, so then both of these benefit massively, and from the column storage, and reading fewer columns means less in IO operations, right? Reading kind of homogeneous data, that means all integers in a one column compresses kind of a better in modern technologies. Okay, so that's why these combination of technologies can make it kind of 100 times faster in row than the row based formats. So just keeping in mind this kind of the Parquet, the file format is the one actually it's pretty much good in IO efficient, because the reason behind that one is they are stored in a kind of a column oriented format. And yeah, so these are RC files, and again, it's a column oriented format that divides data into row groups with a column side, right? So that means actually it's called row groups, right? That means each group, the data is then stored in a columns. That means so at the kind of a host level, right? So file is kind of a row grouping, and then but a fine level, the data within this group is kind of column. So good for kind of column pruning and compression. It's a hybrid structure is the one that is a much important fact. Okay, so then the caution is actually it's does not evaluation on schema or adding a new column requires rewriting file, those kind of stuff, right? So this is called a record column file, and this is for ORC, right? Optimized row column. So it's a evaluation of RC file, and it built on RC file. That means ORC is considered as evaluation of the RC file format and inherit all the benefits and kind of stuff, right? So yeah, so actually I think uh, this is the thing, right? For your syllabus, it's only need to know about the Parquet, right? But I added kind of RC file ORC for your reference. Okay, so that's why I did go through deeply. So if you want to have an interest on this kind of topics, so you can review on that one, right? So mostly again, I would like to say I added the content, kind of deep contents that I want to have a kind of a match my this lecture series kind of an industrial level. So basically, well, in a kind of syllabus, what you are from expertise kind of just need to know about, okay, what is Hadoop, and what is no mean by MapReduce, what is mean by Hive or Pig, then what is mean by those kind of concepts only you need to know, right? But if you are now we are in a kind of a different world, right? The AI world. So if you are kind of find a job on kind of this data engineering side or the analytical side, so the extra knowledge is the key that you can find it pretty much easily, right? So based on that one, that's why I added I kind of these kind of in-depth concept, the file type, REC file type, ORC. So these kind of stuff I include. So for knowledge, it's only the Parquet is the one that where I need to teach on you, but I added extra knowledge on you. So that's why I didn't explain pretty much kind of in depth these concepts, because if you interested on that, you can just type in a kind of a chat GPT or stuff and just find it what's in there. So this is the one that you need to know about well, right? The Parquet one. And so then again, yeah, so these are the things, the file common file formats that we used on the Hadoop ecosystems. Um, okay, now the streaming one is correct. Okay. Uh, okay. Now let's move to the streaming. Okay, the stream and the pipes. So, okay. So in here, this is the thing, right? So we can use any language that can be read, standard operations in, and write the standard out, right? So that this is the why we can write the map reducing language. So in early I would say that it's a Java, right? So but um let's say that you don't need to know Java to write MapReduce program, right? So if you can read from standard input and kind of write to kind of a standard output, then you can use Hadoop. Okay, so that's why this is a kind of a big idea. You just need to know what is streaming and pipes. That's the only thing you need to know for now, but I'll try to explain kind of much deeper context. Okay, so the big idea is actually Stream is a kind of a utility that built into Hadoop that lets you provide the mapper and the reduce script in any language, right? Kind of Python or PHP, per kind of stuff, right? So as you long as a kind of a script is read in input from the standard input and write in the kind of a standard output, the Hadoop can use it, right? So these works become kind of a Unix style, right? That means standard input and output is the one of the oldest, but it's a kind of a universal interface in computing, right? So, every reasonable programming that language can read it and put into kind of a output, right? So using that bridge, the Hadoop actually it opens a kind of a itself to virtually for every language, right? That's why this is a kind of a much important, right? Don't need to know about the only the Java is not the one that you can write it, but you can use the many kind of language like Python kind of stuff with the help of standard input and standard output mechanism that every language is used on. So built off on that one, Hadoop actually solve this problem, right? So many data scientists actually they know about the Python or are not Java, right? I think in the statistical courses in the university. So I think the student who follow that the statistical stream, there's a course in the university related to R and Python. I think, yeah, R and Python they follow that one, but not the Java, right? So that's why actually the Hadoop try to make the adaptation. So then many web developers they know the PHP, right? So then many kind of system admins, they know about the shell programming, kind of Perl. Okay, so then the Hadoop, what Hadoop is doing is Hadoop stream them all in a kind of a writing the Hadoop jobs without learning the Java, right? That's a kind of a very a kind of a experimentation drop in a kind of a stuff. Okay, so the reason behind that one is actually the Hadoop team actually they found that this has a kind of a gap, and they introduced this the Hadoop streaming for solve this gap, right? So so this is the one, the run map reduce in any language, right? You can use non-Java or Java, right? So that means the streaming actually lets to create or run map reduce script in any language, right? So then the other one is the default is the Java one. That's correct. So basically Hadoop map reduce framework written in Java, and supporting map and reduce programming in a kind of a stuff, right? So then API, I think you know about the API, right? So application program interface. So Hadoop products actually API to read the MapReduce program in languages than Java, right? So they can it's a not a kind of a official hat, actually it support the kind of a programming infrastructure. So then it executable as a worker, right? So streaming is a kind of a utility that map reduce jobs with the script or executable as a map or kind of a reducer one, right? So then other thing is actually you need this stream as a beach. That means the interface between the Hadoop and the script that you are written on, actually it's a kind of a classic Unix pipe, right? Model. The Hadoop pipes input lines into a script, then script pipes will output the lines back, right? So a stream actually separate two concernation. Hadoop handles the distributed orchestration, splitting data, scheduling tasks, recovering from failure, and shuffling the gap between map and reduce, right? So the script that we are writing, it handles the actually transformation logic, right? So it can be like this, right? Give me the input line, then what it will do, right? So we need to think about the logic, and Hadoop manages that one inside the cluster. That's why this is a kind of an important kind of a concept. Um, Again, it says that these are the language supported, and this is how the stream is working actually. So okay, here's the thing. Now the thing is actually first thing is input format, right? So what Hadoop will read the input data and package each record as key and value pair, just like in the map reduce, right? So then other thing is mapper. That means standard input and standard output. What happen is Hadoop convert the each and key and value into kind of a tab separated line, then writes the mapper into kind of a script standard input, then the script is processed it, and then write back to a kind of a lines on the standard output, right? The other thing is actually reducer, right? So then the shuffle group, right? So what reducer will do it for each group key. Hadoop writes the line into the reducer's script. Then typically one lines per key and value in groups. They can repeat it, right? So the actually the reducer is the one that reduce the script and accumulate the files and kind of line standard output. Then the final thing is Hadoop write the reducers output into standard HTML, and the sorry standard output into kind of HDFS format, and output the file into that one. So that's the kind of how the stream is working. So first thing is input format, then the mapper actually same thing, the Hadoop will read from the standard input, and again it will do the process for mapper and write it into standard output. Then again in the reducer one, it reads from the standard input one, and then again is read onto the standard output, and then finally, after finalizing the map and reduce that process, then it will finally write into the kind of a HDFS format. So that's why it's a kind of a genius design actually. So Hadoop owns the cluster orchestration, then the script owns the transformation logic. That means the script that we write, it includes the transformation logic kind of reading lines and emitting lines. So then the Hadoop orchestration, it contains the splitting input, scheduling, fault tolerance. So these two communication, only two kind of communicated with this, right? Standard input and standard output. And this is the one of the clean interface design in a kind of a distributed computing, because it use a kind of a old kind of a 50 years old, I think, maybe Unix idea, right? The pipes actually. So that's a kind of a this to kind of a new brand, kind of a new evolution of the technology, right? So okay. And this is a kind of another in-depth concept, right? So then so let's work through the kind of what's mapper script file looks like, life looks like, and kind of a stream job, right? So first thing is standard input and output, right? So what the thing is actually, mapper script reads the input line by line from the standard input, and it emits the output to the standard output, right? Nothing more, right? So the mapper and the reducer, the script that read input line by line from the standard input, and it emit the output to the standard output, right? So then other thing is actually job cycle, right? Managed by the utility. That means the utility create a kind of a map and reduce job and submit it to the appropriate cluster and monitor job progress until it completion, right? So that means what it happen is the script does not need to know any of that one. It just run, right? So the other thing is actually each mapper task launches the script. So when the streaming run your job, then the each mapper task launches the script as a kind of a um, brand new separate process, right? So that means the kind of process it share of the input and then exist, right? So they can be hundred and thousand of mappers, kind of mapper script process running across the clusters simultaneously, right? That's why it say that when the script specify the mappers, the each mapper task launches the script as a separate and process when the mapper is initialized, right? That's what it means actually. So other thing is actually line in and key value pass out. That means the script read the input lines and like a kind of a key value pair and process them and write the output line into shape, same shape, right? A kind of a key and a kind of a value and kind of stuff, right? So then it collects the line oriented output from the standard output and convert the line back to kind of a into a kind of a key value pair. So that's how the mapper script does inside that one. And the same thing the reducers also, right? If you are talking about the reducer, it launches the script. When the reducer script is specified, then the reducer task launch the script as separate process, and reducer is initialized, right? So that means that when the reducer script is specified, the reducer task launches and it separate as it a separate process, and same model as the mapper. So then same thing, it's a standard input and output dance, as the reducer task run, it converts the input key and the value into a line and feed them into a kind of a standard input, right? So it gathers the, line oriented output from the standard and convert each line back to the key value pair. So then tab is the separator, right? That means for by conversion, the prefix of an input or output line that up the first tab character, and for both mapper and reducer, the prefix of a line that the first tab is the character is the key, right? And this is small but important practical detail when writing the real streaming jobs. Okay, so that's a tab is a separator, and so whole line has a key, right? So if the line contains no tab character, something like that, the whole line treated as a key and the value is none. right? So this is the default behavior of the customizable via the input format and the output format options. Okay, so and so this is the Hadoop pipes, right? Um, okay, so there are four facts that we are talking about Hadoop fights. So the first thing is actually Hadoop is a kind of a non-Java interface, and it is this time it's especially for C++ one, right? So C++ interface to the Hadoop MapReduce, okay, and so first thing is actually the Hadoop pipe is official in C++ interface to MapReduce, right? So it exists for organization where existing code base like C++ are written in everything instead of Java, right? So the other thing is socket, right? The socket not the standard input and output, right? So unlike streaming, it uses the standard input and output. The pipe use the socket as a channel between a task tracker and a C++ mapper, right? So that means the pipe this is a kind of a tight and a faster integration, and integration with the kind of a binary structured data. So the other thing is linked again C++ library, right? So that means the application links again Hadoop C++ library, and that means it's a kind of a thing wrapper for communication with the task tracker child process. So then other thing is actually extended mapper, right? So that means you define the mapper and reduce function by extending C++ classes, but the Hadoop by namespaces and implemented map and reduce methods, right? So it's very similar like kind of Java API, but the whole thing are actually in kind of C++ in there. So, right? So the core summary in here actually the pipes shows the Hadoop non-Java integration. It was not a kind of a single mechanism. Stream is kind of a lightweight language acoustic path, but pipes are most tightly integrated path especially for C++ language, right? So the platform offered kind of a choice because different organization has different needs. That's the kind of what the Hadoop pipes that we need to know about it, right? And yeah, so these are the kind of stuff actually, and this is the context of that and byte buffers, and whereas the C++ application starts, so these are the kind of stuff, right? So so at the key point in here, okay, so there are a lot more things to know about Hadoop, right? And I know that is I think sometime you didn't understand this concept in depth, right? So what I need to know only is if you are so in your syllabus, actually the you would know about only the kind of what is MapReduce, what is HDFS, then what is Hive and Pig built for, and what is Parquet, and what is mean by Hadoop pipe and stream, right? Those 5 points actually you would not need to know about it, but I include kind of in-depth concepts. Uh, Again, the reason behind that one is actually I won't know about the not the kind of I'm not focusing of the exam oriented teaching, right? Because I know that you are ready for exam, then write it, then after some time you will forget the concepts, right? So, but the thing is, if you are kind of facing an interview, so that's not the thing ideally it asks for, right? They ask for kind of different stuff, right? So they want to know how depth you are in, how you are knowledgeable in that kind of stuff, right? So that's why I added a kind of a in-depth concept, kind of a to explain. So other rather than the expectation is a kind of a so at a kind of one side for Hadoop streaming, and other one is at a one side for Hadoop piping, right? So those are the expectation, but I added kind of another extra knowledge for you. So in that case, you can read it if you need it, and kind of in-depth concept sometimes it's harder to I know that it's pretty much harder to kind of understand this stuff, but the important fact is know about the kind of a base knowledge. The reason behind that one is in the interviews they will ask, if you got a problem like this, what's the tool that you are going to use, right? That's the thing that they will ask from you. So then again, I would like to say, if you are doing kind of a self-learning thing, so it's read this one, and if you are not kind of a much more um kind of a you know uh, familiar with this kind of stuff, just find in the kind of a chat GPT or AI tool. You can have a kind of kind of a good explanation with examples, right? So that's the thing that we need to talk about the mm, you know Hadoop. And so yeah, there are, now we talk about much more things, right? So from the beginning, actually, wait a minute. Okay, so we considered about what's Hadoop, the HDFS, MapReduce ecosystem. We talk about file system and streaming pipes, right? Those are the things. So, but ideally, again, I would like to say these are the only things that you need to know about, right? So in your syllabus, these are the things that it includes actually. So, but I added kind of extra two topics as well. Um, okay. So far actually from the beginning of this lecture series, we talk about the kind of introduction to big data infrastructure, what is 3V and 5V kind of stuff, right? Then next lecture we talk about NoSQL. So why is the NoSQL is suitable, and what's the reason behind that when the traditional databases are not sufficient for big data processing and stuff, right? Then the next lecture we talk about the HDFS, right? So we talk about this HDFS as a kind of a one another lecture series, right? So then we talk about the you know HDFS. Then we talk about the data warehousing, right? So I try to explain the data warehousing, the basic concept from the beginning, and I showed you a kind of example behind that one, kind of how to create a traditional data warehouse using SSIS tool using Visual Studio. And then other thing is we talk about the Hadoop fully ecosystem, right? So I know that you have to know about these concepts, okay? So then the concepts will drive you to kind of a practical knowledge. So that's why I try to give an understanding about the Hadoop, what is Hadoop, and what are the MapReduce model and the ecosystems and the languages and kind of stuff, right? So now let's take a kind of a 5 minute break and let's move to the other lecture. It depends on the Apache Kafka, right? So give me 5 minutes actually. Okay, I will quickly share my screen. Okay. Okay. Can you guys see my screen?
Yes, sir. Yes.
Okay. Okay. So now, so these are one of the most important as well as a kind of a interesting topic, right? So if you are um, you know, dealing in the kind of a more kind of a system, this technology is kind of much more important. And I will try to give a kind of a um, you know kind of a concepts behind this one, and what is Apache Kafka and kind of a stuff, and what is kind of a pops up pattern and kind of stuff. Since you are in the industry, it's pretty much easy important thing, because everywhere in the kind of a system, this technology is used enough, right? Okay. And it's a kind of a most important pieces of the modern software infrastructure, right? The Apache Kafka. So when you heard about this one, I promise that that means most of the system it depend on it, right? So kind of when you kind of um, for example, right? So if you are getting a kind of a real-time notification in your phones, so when your bank is kind of a flag suspicion transaction within seconds. So there's a kind of a model behind this kind of system integrations, right? So that's called PubSub, and the kind of the tool that we are using is kind of we are talking about in here. It is Apache Kafka, and there are much more tools that we can use instead of Apache Kafka, right? Kind of Azure Service, Buster Weeks, kind of stuff, right? So sometime that's why I'm telling that. So the system that you are experience on kind of, let's say, the real-time notification in your phone, that means again, if you are subscribed to kind of a YouTube channel, then sometime in your phone you will get a notification there's a kind of a new video, right? So those kind of system behind this one, the engineering is kind of a PubSub and the Apache Kafka. In here we are going to talk about it, right? So now we will try to build everything from the sketch, right? So if you are kind of a beginner, so that's okay, right? So if you don't use Kafka before, so by the way, let's begin it from the zero layer, right? So then so we are going to actually talk about how the kind of traditional systems are talk together each other, and how the classic request response model. Then we will see the problem behind the kind of request response model, and we will discuss uh, the the way of communication by kind of event driven model. So I think that's other one of the key important thing, the event driven one. So then we look how the companies move from the event driven system. So then the other thing is we will talk about the Apache Kafka and the main pieces, kind of producers, brokers, compute consumers, and we will dive into kind of topics, partition, offset, and kind of stuff, right? So actually, by the end of this lecture, you will get the kind of idea about the Apache Kafka architecture, right? And you will be able to explain every pieces, right? So so let's move to the lectures, right? So this is request response model, right? So then I know that you are familiar with that, right? So on the right we have client, so on the left we have server, right? So client send in something and it send a request, and then the server answer you know um answer this response, right? This is pattern actually everywhere, right? So then um you know let me give a kind of a example, right? So ordering the food, right? So you sit down and waiter comes you waiter comes for you, right? And you would say, okay, I would like to buy pizza or something like that, right? So that's a request, right? Then the waiter goes to the kitchen and then comes back with the kind of stuff and and puts the pizza in front of you, right? That's the response. Okay, so right, that one you ask, they answer, right? So that's the dealing with the kind of the traditional pattern, right? The computers do the same thing, right? So when you type the google.com something like that in your browser, the browser is the client, right? So then it sends the request to the Google server, and then it server asks, okay, please give me the home page, and Google server thinks, um, you know, um, find it, and then it sends back the response, right? So that's the thing actually we are talking about in this one. But the thing is actually this pattern is common, that is being formalized for protocol HTTP, right? The hypertext transfer protocol, right? The thing is actually the hypertext transfer protocol is essentially for rulebook for request response on the web, right? So every time you click a kind of a link, and if you scroll the Instagram or log into email, somewhere underneath the HTTP request is going back, right? So that's the thing actually we need to talk about. Um, you know, there are three characteristics actually in this model, right? So actually, one thing is the word synchronized, right? That means happening at the same time, right? But in computer really mean it client waits. Okay, the client send the request and then stop it, right? It cannot do anything else useful until the response is arrived, right? So in the second one is one to one, right? That means the client talks to one server, then the request go to a specific address, then the response come back at the same place. Okay, so that's the kind of idea actually. I just uh, have a kind of, I just want to know about the idea of this model, right? So this is the classic synchronization communication pattern, right? So, okay, so then we have kind of gaps in there, right? So with this, why the synchronization model breaks down at the scale, right? So one problem is it's bad for multiple receivers, right? That means the request response model is kind of fundamentally to one conversation, right? So imagine that you run a kind of online store, then the customer places an order, and single even order place, it needs to be known by at least five different part of your business, right? For example, the data warehouse, needs to know, so then they can pack up the inbound. Then the shipping team, then they needs to know what they can plan delivery, and the billing team kind of stuff. So they need to know about the credit card, and the, marketing team wants to know, the analytical stuff and kind of stuff like that, right? So if you have only one request and responsible, what happen? You have to send five separate calls, right? So one to the data warehouse team, one to the shipping team, one to the billing team, kind of stuff, right? So that's the five places where things can go wrong. Okay, so the five places, that means five places mean that in this example, I'm telling kind of a five places. One team is kind of a again, I would like to the example, one team kind of a data warehouse team, right? So the shipping team, billing team, analytics team, and the CRM team, right? So then if that's the five places that where things can go wrong, right? So then the every time the one one team will ask, okay, hey, we also need to know about the orders and kind of another stuff, right? That's do not scale. That's why it's bad for multiple receive, right? A single request can go on one server, but the broadcasting many will request in separate of calls, right? So other thing is it's tightly coupled, right? That means we talk about this already, but imagine that the kind of a data warehouse system decide on upgrade, the change is the structure of the data that they accept, right? Maybe they used to take an order ID as a number. Now they want to it as a string, right? So what happened is actually everyone who called from the change to their code, the every system that need to know about the now the data warehouse is broken until it updated, right? So that's why actually it's a tightly coupled one. So client must know the server address, API, schema, availability, and everything is done, right? So the third problem is client waiting. So that means so the thing is actually when the client send a request, right? So then it blocks until it gets a response, right? So that means a single conversation, that's fine, right? So a few hundreds of milliseconds, right? Not a kind of a big deal, but if the server is slow, what happen is if had to do is kind of a database query or kind of it will take 5 seconds. Now the application is kind of frozen into 5 seconds, right? So for example, let's say if I want to fetch the data, then there's a kind of the query will take around 5 seconds. Then the application is slow, right? So then if we multiply by it kind of a thousand of user, the actually the application is kind of a frozen, right? So that's in the industry you will have this kind of stuff, right? So then actually there are actually there are tricks to that mitigate this kind of state stuff, like kind of asynchronization, callback states kind of stuff, right? But they are actually a complexity, right? So then the fundamental issue is that the response request model, right? The client and server kind of stuff waiting, okay? The other thing is actually web service chaining, right? That means the reason behind that one is actually this is the kind of teams that move for the build the microservices. Okay, so service A calls B, C and D, right? So that means latency is next, one failure cascade through the chain kind of stuff, right? So imagine that we have a kind of a service called service A, right? To answer a request, it had to call to the service B. Then service B has to call to the service C, and C has to call to the service D, right? So so imagine that service A is the one we need to take the answer, but for the answer in the that request, service A should call to service B, then service B should call to service C, and service C call to service D, right? It's a kind of a chaining, right? So A is calls to B, B is calls to C, calls C is calls to D, right? So now each call at a kind of a bit of latency as well, maybe kind of a, let's say 50 milliseconds to each and time. So by this time you will get back to his a answer. So you have to spend around how much? 1, 2, 3, 4, right? 50 milliseconds to wait to chain it and give the answer, right? So the worst part is actually the latency. Let's keep it for now, no. But the worst part is failure, right? For example, if D goes down, if things that the D goes down, then what will happen is the C cannot answer, right? C cannot answer means B cannot answer, right? So that's called kind of a um, you know uh, the reason behind that one is kind of a the fail in the whole system, right? So and it's the one of the kind of a incident that can happen in the distributed system, right? So for this one actually we need to address these kind of problems, right? So that's why we are moving into a kind of a event driven model. Okay, so in the traditional architectures, so we need to address this problem. So we need to move a kind of a model called event driven, right? So this is called event driven one, and so there are three types of things. Right? One is generator, other thing is actually distribution layer, other thing is consumer, right? So the key idea behind that one is actually it's decouple, then asynchronous and one to many deliveries, right? So these are kind of let's say kind of a different way of thinking about the communication between the systems, right? So instead of one system asking for other system to do this, one system is kind of you know, then kind of, let's say, ask for something in the world, and anyone who is interested in listening it, then they can provide it, right? Instead of a request and response model. So we have events and reactions instead of request and response, right? So keep remember again, in the event-driven system, we have events and reactions instead of request and response, right? So then I I found a kind of example, right? So think about a kind of a newspaper, right? So since the uh, you know um, many less people now read the newspaper now, think about the website, right? So newspaper does not call every morning and ask you, here you do hey, do you want the today's news, right? Basically newspaper does not like that, no. So what we are doing is, we are going for the kind of a shop and then buy a newspaper and then we read it, right? Otherwise the newspaper does not ask, so okay, what do you want to know about today's news, right? So that would be a kind of a equal, much more equal to kind of a request response model, right? So instead of that one, if we have used a kind of a news website, so then the instead of newspaper write the news once and it published on an article, anyone who is interested and come and read it, right? So many readers from the one article. So if a new reader show up it tomorrow, the newspaper does not have to do any extra work, right? The article is just in there, right? So likewise, so it's a kind of a stuff, basically what we are dealing with, right? The producer publish events, the broker fans them and out for all interested consumers, right? So now look at, if you are looking at the picture, so the left thing is actually we are calling as generators, right? So these are the system that produce events. Okay, so they could be server login activity, IoT sensors, or kind of checkout system or order system, stock exchange kind of stuff, right? They generate events, and each event is kind of a small kind of data that would say, okay, one thing is happened, right? So then, so for example, let's say YouTube, right? So YouTube actually, if you subscribe to this one, then it will, if you publish a kind of a one um, um, a new video to that one, that channel, it's a kind of a event, right? So then in the middle of the distribution layer, this is the kind of a, let's say, magic piece, right? So it receive events from the all the generators and hold into them and distributed them, and it will send to the anyone who is expressed that interest, right? So that means, so we are the people who interested in YouTube channel, right? So it's a kind of a YouTube channel. We are the people who interested in, right? So finally, we are the consumers. So then what we have to do it, we have to subscribe it, right? We have to click the subscribe button. Then subscribe button means we are interested on that YouTube channel videos, right? If a new YouTube channel video is uploaded to that channel, then what will happen is it sent an event, okay, here we are then the channel is kind of publish a new video, then the distribution layer will actually sends to the consumers. That means we are getting notifications from the YouTube, okay, here there is a kind of a new video, you can because we are interested on that YouTube channel. Now we will get a notification, okay, now you can start to watching, or there's a kind of a new video is released, right? Same thing happening here, right? So actually these are the consumers, right? So then there are system who want to react to that events, right? The billing system or analytics they bought from the previous example, that they sit on the right end of the picture, right? So they subscribe to event and they care about it, right? So that's the, now if we compare this one with the request response model, the generator does not know who are the consumers, right? They are decoupled, right? So basically, there's a layer, right? So the generator doesn't want to know that one, right? So actually, the YouTube channel who are doing the YouTube channel, they just publish it. Okay, so they publish the events actually. So I think they do not know to concern about who are the consumers, right? The consumers are the who are the who are the kind of sets that who are interested in the on their channels or kind of stuff, right? And then it just a kind of a published event, and the consumers don't know who is the generator, right? They just receive the event of a certain kind, and two sides have been decoupled in a space, right? So that's why it's called they do not um, each other addresses, and they do not have need to be running on the same moment kind of stuff. Okay, so so that's the kind of event-driven kind of a model explanation. And these are the kind of key factors we talk about this one as well. So first thing is actually loosely covered. The producers don't know who are the consumers, and consumers don't know who producers. Each side involved in independent, right? So other thing is offline tolerant. That means the message are persistent, right? So consumer can be offline and still they will receive an event when they are reconnected, right? For example, think about the YouTube example, right? So when we are going offline or we are in the airplane mode, so definitely we are not receiving the any kind of notification, right? If you are turn on the kind of connected to Wi-Fi or kind something like that, then we will receive the notification, right? That's why it's a the messages are persistent, right? So if you are going offline, are the messages is kind of destroyed or not? No, it's not like that, right? The messages are persistent, and when they are kind of reconnect, we will receive the events, right? That's called offline tolerant. So otherwise, this delivery semantic, right? That means actually, um, you know, um, this is the kind of a technical term for question like how many times that kind of each just even reach the each customer, right? In the ideal world, the exact answer is exactly one, right? So each event arrives at each interested consumer actually exactly one time. But in the real world, sometimes the network failures, restart, crashes. So then the exactly one is a kind of a hard to guarantee, right? So we ended it actually three common modes, right? So the at most delivery means actually, so this is the at most one, right? So that means at most delivery means actually the event is delivered to 0 or 1 time, right? So in the other word, the system never duplicate sends the duplicate one, and if something goes wrong, the event must be lost, right? This is fine for time something like log messages where losing one is a kind of a not a kind of a big deal, right? So for example, let's say so there's something that's not important for kind of notification for sending another time. So then so it's crashed and the messages can be lost, right? That's called at most delivery, right? So other one is actually at least delivery, right? So at least delivery is a kind that which means that deliver one or more times, right? That means the system never loses an event. That means it can send kind of multiple duplicates if networking kind of causes retry. And sometimes in the bank system you will receive the same message couple of times, right? So that's the kind of stuff um at least once delivery, right? So then if you have already processed that one, no need to you will skip that one, right? So the other one is actually exactly one delivery, right? Which means uh, the event is exactly one time delivery, right? No loss, no duplicates, and this is a um, kind of a Kafka and sometimes kind of a careful configuration, right? So what you have to do is you have to exactly one for use cases, right? So that means let's talk about that one later, but you must think that there are three delivery semantics, right? One is exactly one delivery, at least one, at least once delivery, and at most once delivery, right? Those are the things that we need to talk about, right? so then so these are the kind of software platforms or event driven apps, right? For example, if you are looking about the Kafka, so that's what we are going to talk about. And so then we have Apache, Pulsar, RabbitMQ, ActiveMQ, then Azure Event Hub and Oracle Streaming, the Event Kafka and Panda. There are a lot more technology that we can talk about it, right? So actually, this is for your reference, right? So then, so the Kafka has become the de facto standard for high throughput event stream, right? So what do you mean by de facto, right? So de facto means in practice that's the one when you read a job description and when you read the engineering blocks, when you look at the architecture companies like Netflix, Kafka is everywhere, right? Kafka is just a kind of a good achievement, right? So that's why it's kind of a it's in practice it's many people to use it, right? So okay, and and these are the actually technologies that's rich for and competitive ecosystem, right? So it's better to find it what is Amazon needs is and these kind of stuff, right? And okay, so these are the common use case for event driven platform, right? The first thing is managing events, right? So that means actually some events are things that did happen, right? So sometime that would have something happen but it didn't, right? For example, the nightly backup did not complete, right? So that means something happened or didn't happen or other system should know, right? That's called the managing events, right? So second thing is state changes, right? So an order place or user sign as sensor cross threshold, right? That means almost every system in business has a state, right? So and for example, an order goes from placed, then it moved to kind of paid, and it moved to kind of pay packet, and it moved to kind of shipped and delivered, right? So that's the status, right? For example, if you order something from the kind of a Daras or something like that, if you check on the status of the of that parcel, you will see those status, right? That's called status change, right? So placed, paid, packet kind of stuff. So each transition is a state change, right? So each one is a kind of a interesting to kind of a customer. That means the changes should know, right? So that means the publishing each stage change is an event and it lets you to build a kind of a system react on data, right? So that means for example, let's say that so change the kind of order when the order is placed it if it move change the state from place to paid or place to kind of packet to shipped kind of station, then you will receive a message, right? Or you will receive a kind of an email. Okay, so it's totally shipped, and please look in for the kind of a delivery process, right? That's kind of thing that can be happen, right? So other thing is actually yes, trigger notification, right? So you know that when condition is met or fire, then we can alert it, right? So the other thing is IoT data ingestions. So that means million of devices is streaming telemetry into a kind of a central pipeline, right? So that's a kind of a important use case event-driven platform, right? For example, if you have weather data, so it will push to a kind of a one centralized system, and when they are receiving, so it will process and show to us, right? For example, kind of a AccuWeather something like that. So the IoT sensors in the everywhere in there, it will push to a kind of a streamline pipeline, and then it will push the telemetry into kind of a central pipeline, right? This is CDC capture. So we talk about in the data as in the CDC, change data capture, right? So every streaming, every insert, update, delete from the database as it happened, right? That means we are having a kind of a record where the historical record also keep it, right? The change data capture actually. So it's a kind of a powerful in the kind of a, imagine that we are in a kind of a transactional database and say that we are kind of a customer records in the system. No, every time who updates that customer record, that change CDC capture an event and publish to a stream, right? So that's kind of stuff that can be happen, right? So other thing is near real time analytics. Okay, so for example, the collect the data all day, then batch process overnight, and in the morning we can have a kind of a explanation of the yesterday's data, right? Like a kind of a weather related kind of data, right? For example, today in the news, there is a kind of a news related to that yesterday the high rain um, for the kind of candy or something like that. They process it, right? So what will happen is a kind of a near real time analytics, right? Process data, it arrive and then kind of a process it and then shows us, right? So that's a kind of a stuff they are doing, okay? And you know, these are the events that we can use it. So the real-time analytics and CDC, IoT data injection and trigger notifications and stuff, right? So the process data as it arrives. So for example, there's another example, the fraud detection for the cards, right? So fraud transaction. So when something happen, so if you are putting a kind of a card which is not acceptable, then you will receive a notification, right? Okay, now there is a fraud decision that is going to happen. So if we send it tomorrow or something like that, the transaction is already completed. That's not a kind of a advantage on that one, right? That's why the real-time analytics is kind of much more important. So let's talk about the web APIs, right? So it's a uh, kind of a I would say a kind of a extra knowledge for you, right? So the web APIs, right? So if you look at it, the picture, um, you have US, right? So for example, the mobile app, then web browser. So we have the mobile app using API gateway, right? So the web browser using web app and it communicate with the same services backend, right? So this is a kind of a common architecture in modern companies, right? So this is called actually microservices, right? Instead of building giant programming into everything, that means the inventory service, delivery service, account service, all are not in a kind of a monolithic way, right? So that means monolithic implementation. That means all the codes are not in a kind of a single code baseline, right? So instead of that one, so it will build many small programs that each thing to do one thing, right? And it will talk each other over network, right? For example, the inventory service talk with the kind of a delivery service, right? So the delivery service kind of connecting with account service, right? So these kind of each and every microservices, they will communicate each other, right? So throughout the network, right? So that's why actually the advantages is the kind of the small services are there's another advantage, right? So the small services, they are easy to understand, then easy to test and deploy independently, right? So that means actually the thing is actually, for example, let's say that the engineer who has kind of a has a background of the account as well, so then it's we can allocate this service implementation to him, right? So then he can build this service independently, test it independently, and then deploy it independently, and they can expose the API to communicate with each others, right? I think definitely you will have the experience on that one. And there's a kind of a disadvantages as well, right? So for example, there will be loss of communication, right? So then sometime if the communication is not kind of uh will if it go wrongs, then there will be a kind of some parts of the reach of that system will go down, right? So that's why there are pros and cons for microservices, but definitely, you will not need to know about the what are the microservices and why is used for that one. What are the advantages of microservices architecture? then those kind of stuff, right? So because industry, in real industry experience, what we had to do is definitely sometime you will allocate into a kind of a team which is built for kind of an inventory size. Okay, so such kind of things. Maybe I think the 5 to 10 members are the kind of the for a kind of each microservices, designing, architecturing, implementing, kind of testing one, right? So again, I think there's a for extra knowledge, there are two types of tests, right? So integration test and the other one is unit test, right? For those kind of tests, we can use for test these microservices as well. So then, so that's why actually this is a kind of a much more important concept about the the web API as well as the microservices, right? So the most common way of this service talk is web API. So usually REST API, sometimes GraphQL as well, gRPC, right? So then, for example, service A call to service B over HTTP and ask for some data and get a response, right? So this request response model, as we started, is just applied internally, right? But there's a kind of a limitation as well, right? For example, if we have more calls, that means, for example, let's say like this, right? So there are some limitation on that call as well, right? So the latency actually, what will happen is, so let's say that service A calls to service B, right? For same type of data. For example, let's say that student ID 1, so then the service asks for data for student ID 1 from the service B, right? So every time if we send the HTTP request to that services, what will happen is latency can be caused, right? Because we need to wait kind of, let's say, 50 milliseconds, right? So instead of that one, if we can add the kind of a caching mechanism, so then what will happen is that will be kind of a much more improvement in the performance, right? So then caching is the one of the most important factor for having the kind of increase the uh, you know increase the kind of a response time in the web API, right? So for example, let's say we can use NoSQL database, right? So remember Redis, right? So we can use the Redis as a kind of a caching mechanism, and we can add key as a student, and the student record the JSON student record details and the value, right? So then instead of um, calling to that service B, we can retrieve the data from the cache, and then do the process and serves to the request, right? So that's the actually kind of drawbacks for the kind of the microservices architecture. Definitely, the idea behind that one is, instead of building each and every services in a kind of a one monolithic pattern, the microservices is much more ideal. So there's a one other thing is, so let's say that uh, if we think that all three services are implemented together, what happen if you push a kind of a code chain related to delivery service, and it will break? What happen is, if we are building all together, the entire system will goes down, right? So that's a kind of a disadvantage for kind of one of the major disadvantages if you are using kind of a monolithic tree. Okay, so the reason behind that one is actually the all together all the system will break up. So for example, say that I think in here, let's say account service, right? So we need inventory service and delivery service. These are the two more important service, right? Let's consider as this. But account service also much more needed, but not much the kind of important features delivery, right? So what will happen is, if you push a kind of a code change to the account service to place where all the things are built together, then it will break the system. It will crash the system, right? So the entire system will goes down. So but what will happen if we use this microservices pattern? So if we use inventory service deployment as an independent way, then the delivery service also independent way, account service also independent way. So then if we push the changes to the account service, then it will not impact to delivery service or inventory service, right? These two features will be up and running, and definitely this service will goes down. So it's better to have a kind of having this kind of components up and running, and in the kind of crashing this system, right? The account service system. So that's a major benefits and the major drive that the moved from the monolithic architecture to the kind of a microservices architecture. So that's a kind of a thing that you should know about the thing. And this is a kind of a point-to-point pattern, right? So each service and depend on other services. That means each services depend on directly on others, right? So for example, these are the four colored of the microservices, right? So which is kind of a connecting every pair to each other, right? So that means so the four boxes and the four lines, they are communicating in everywhere, right? There are six connections, right, all together. And they are bidirectional, and they can count even higher when you about to calls who to in, right? So that's the kind of stuff that will happen, right? So this is a kind of a actually cost of point to point coupling, right? So you can see this service called this service, right? So it's a kind of a highly coupling factor, right? So uh, yeah, now it's 10:05, right? Okay, I will explain it. Let's have a kind of a break, right? So let's meet on 10:25, something like that, and then let's have a further discussion about this one, right? So then at 11 o'clock, let's have a start on the presentations, right? So let's have a kind of a interval for now. Hello guys. Yeah, I will share my screen and okay. You can see my screen, right?
Yes, sir.
Okay. Okay. So yeah, we stopped at here, and yeah, we deeply kind of talk about the microservices, its advantages, and kind of its stuff. So now this is a kind of a place where microservices um kind of in a kind of a disadvantageous points, right? So this is called a point to point pattern. So this means actually you can see these are the microservices for microservices, and it shows that each and every pair it's communicated each other, right? So for example, in here there are four microservices, and so if we talk about this one, they are communicating kind of um, 1, 2, 3, 4, then 5 and 6, and if they are kind of having bidirectional communication, then they are having kind of 12 connections, right? So that's why it's the n service, it's n into n minus 1. That means this n is 4, then 4 minus 1 is 3, then 12 connections, right? 1 2, then 3 4 5 6 7 8 9 10 11 12, right? So that's why they are end up with n 12 connections. And then so this is a kind of uh, services that you know um, they communicate in each other, right? But in practical scenarios, they are not talking each and every service, right? So the if you are talking about the connection is 12, but the real number is usually less, right? So the bigger problem is actually not the count. The bigger problem is actually its coupling itself, right? For example, I say like this, right? So you know, the account service, right? So in the previous example, the account service, they decided to upgrade something, right? So they say that they are moving from a legacy database to a kind of a new one, right? And they say that they want to change their structure of their API responses, and maybe the IDs now kind of properties they will change, right? They will announce us in a kind of a 2 or 3 weeks. They will flipping the switch, right? Then what happen is actually, every service that talks about to account, they need to update its code, right? So inventory service need to update, delivery service need to update, and so then and kind of some random reporting service that nobody remember it exists also need to update, right? The reason behind that one, each and every service it communicate each other, right? The account team can't move the until everyone is else moves, right? So then if it's a kind of a 1 or 2 weeks, maybe it's kind of a 3 week coordination, right? So that's a kind of a advantages, right? That's a cost of a kind of a point to point coupling. So the technical team is that you service having kind of a high coupling factor, right? So in a kind of a world, when one thing changes, lot of other things have to change it with it, right? So then the issue is if the system is closed, then it's a kind of a painful, right? So there is a number cause kind of a distributed monolithic is the one actually this call is of, right? So but actually think about kind of a three or four microservices, right? For example, in that case, point to point is not always bad, right? So if you have three or four microservices, if you change it really, then it's fine, right? But if you have kind of, let's say, 30, 40 microservices, and if you need to add more consumers regularly, then there must be a kind of a better way, right? So that's why we say that the point-to-point pattern is not always bad, but it's at some point, if you have more system is closed off, then there is a kind of a limitations, right? Actually, not the limitation, they are painful points. So this is the reason why we are the event-driven platform as kind of a pops up internal bus for microservices, right? So you can see actually there are three publishers, right? One, two, three, and we can see a kind of a pops up message broker in here and in the middle, and in here the subscribers are on the bottom, right? So you can see the errors goes down from publish then to the message broker, and then again from broker to subscribe, right? So this is kind of a thing that we can smoothly handle that the issue of the previous slide, right? So the publishers on top doesn't connect to everything except broker, right? So the subscriber on the bottom, they are not connected to anything except broker, right? So broker is the single bus that everyone hooks into it, okay? So then this is a kind of a central idea, right? So instead of every service talking to each other, every service, so every service talks only the broker, right? So that's kind of a idea in here, right? So for example, you know, it's a kind of a um kind of a big airport, right? For example, kind of a, let's say, yeah, consider airport kind of Heathrow in London. So it's a kind of a really big, right? So definitely it has a lot of terminals and a lot of airports, right? But in a country of Colombo airport, it's not a kind of a busy airport like London Heathrow airport, right? So in the Colombo airport, we can directly, right? There are a couple of terminals only, right? So we can go directly from one gate to another. So at a kind of that giant airport, they are using a kind of a central monorail, right? So monorail is the one, right? So every terminal connects to a kind of a monorail, right? So then every monorail connects to a terminal, right? So that's kind of a way. So imagine that Yabo tried to kind of build a new connection between every pair of terminal. Then what you should have to do is um, instead of build a kind of a central rail, so they would exactly what happen is the event-driven platform also same thing is doing, right? So so that's the kind of stuff we need to talk in here, right? So so now the thing is actually in in this also there's a kind of a trade-off, right? So if the broker become critical piece of structure, right? So if the broker in here is down, then nothing flow, right? So the broker has to be very reliable, scalable, and very operated, right? So that's why the companies spend on Kafka, and if you commit this pattern, the broker is kind of a beating half of your system. The reason behind that one is actually, you know, so there are some places actually the inbuilt. So there are, we can use the cloud in today's, right? So for example, instead of building our own broker, so we can build our own broker as well. So in early stages, we used to do that kind of stuff. So we can build our own broker, but it's difficult to having features like reliable, scalable, and kind of well operate, right? If we build our own brokers, so we can use the code, any kind of a code that we can build it, right? But nowadays, that's why the Kafka and the kind of the Azure services bus and kind of stuff is came up with, right? So they are made in that one. Only thing is we need to buy that product and then use as that broker, and they are very pretty much sure about the the reliable and scalable and everything, because we have some level agreement on that one. So SLA, means service level agreements, right? So we have service agreements on that kind of brokers, and then what happened is, so we do not want to have build a kind of a broker stuff from the scratch, right? So that's the thing that solution for this kind of communication. And this is a publish subscribe pattern, right? So total decoupling to a shared kind of a message bus. So same thing in here, right? So then so PubSub publish subscribe, right? So sometimes it's called as actually event driven messaging as well. Okay, so this is a kind of much more have kind of much more advantages, right? So then so service actually publish a common message to bus, and then what happened is the other service subscribe to the messages, right? Same thing, right? So the YouTube example, what we talk about, right? So actually, publisher knows nothing about subscribers, and the actually subscribers know about the publishers, right? So they are coupled to each, and they are coupled only for that message format, right? So that's actually what we need to talk about in this one, right? So the service published to a common message bus, then the other services subscribe to messages, and publishers know nothing about the subscribers, and subscribers know nothing about the publishers, and they only couple with the message format, right? That's the pretty much important thing actually we need to talk about, right? So this is actually think about kind of a Twitter, right? So when they back when it called Twitter, right? So the you tweet, right? So everyone followed, you see it, right? So you don't pick who reads each Twitter, and you don't ask for it, right? You just publish it and they subscribe it, right? So this is a kind of a another pops up internal kind of a example, right? So I think mm, yeah. So that's the thing actually we need to talk about. So the other thing is actually we need to move with the Apache Kafka, right? So I will stop right now because I need to wrap up the today's lecture kind of 20-15 minutes earlier. So we can start on the presentations. So actually for now we talk about the traditional request response model, then the request the problems on that one. This is the event-driven model, and we have talk about the key consideration of the event-driven model. Then these are the software platforms for event-driven apps. Then reason behind that why you use that one. And we talk about in-depth web APIs of the microservices, and we talk about what is microservices and how it important for us, and what are the limitations on that one. And we talk about what is point-to-point patterns, and what's the kind of disadvantages on this one. And we talk about the Indian platform and the PubSub subscribe pattern, right? So based in this concept, we can move to Apache Kafka, right? Same thing happening here actually. So I will explain those things in the next day. And yeah, let's start our presentation, right? So I will give you another kind of 2-3 minutes, and then please be ready, and then let's start our presentations, right? So I think group 5 and 9, right? So I think we can start from group 5 and then move to group 9. Let's start it in kind of another 2 minutes.
Uh, can we start, sir?
Yes, you can. Yeah, go ahead.
Uh, Good morning, all. So we are Group 5. So we are here to present Amazon High Available Key Value Store that called Dynamo. So I'm with Ravisha, Tarushi, Buddhika, Tagya, and myself, Lakshya. So let's take a look about our presentation overview. So first we give some introduction and background for this solution. Then we talk about the overview architecture. Then we move on to the core techniques that are used in the Dynamo to uh, make that the expectation. And then we talk about some experience from Amazon uh, when they are using the Dynamo in their production environment. So let's talk about the background story. So imagine you are an engineer at Amazon in the early 2000. So Amazon is growing like crazy. So their customer base increasing, the order, service, all are increasing. So one day your shopping cart services go down. For just 10 minutes, you lost million of dollars. So when you investigate in what happened, you notice that your MySQL masternode was crashed. And the while system was electing a new master, everything was happening. Customer couldn't add item to cart, couldn't check out, just error page showed. So you think, okay, let's add more replicas to MySQL. So problem will solve. Not really. Because of MySQL replication, it still has master node. So when the master is a single point of failure, if it goes down, all writes stop. So user can't add the item to cart. So after that, the engineers closely looking at to the service more carefully, and they notice something interesting. Most of the Amazon services are doing something extremely simple. They save something and they get back those things. As an example, in a shopping carts, they just save item and they get back the saved item. So none of these no need a complex SQL join. None need transaction across multiple tables. They are just doing putting in a value with a key and getting those values. So they ask why we are using heavy relational database for this simple job. We are paying a huge cost for the future we don't even use. So then their key decision moment come. So there is a fundamental distribution system called theorem called CAP theorem. It basically says you can't have both strong consistency and high availability when the if the failure is happen. So you have to pick one. Strong consistency means every read always return absolute latest data, so no exceptions. High availability means the system always responds, even during the failures. So MySQL choose consistency. If it not sure about the data is correct, it refuses to answer. It would rather say error than the give potentially stalled data. But Amazon engineer asks a different question. What is actually worse for the customer? Seeing a significantly outdated card or seeing an error page? The answer was obvious. The error page is not good. A significantly stored card is fine because the customer not barely notice the difference between those two. So they make up with a decision to always respond and always accept the rights and deal with inconsistency later. So they come. This is the philosophy behind the dynamo. So let's move in the next section about the background and designs goal. So as I mentioned, they have to pick one, consistency or availability when a failure happens. So in the Dynamo case, they choose availability. To achieve that, they use some techniques. We will talk about the techniques in the later of the presentation as well. So first, they need the incremental scalability. So they need to add more nodes with minimal disruption to other nodes. So for that, they use something called consistent hashing. And the symmetry, that means every node had equal responsibility. So there are no master node that no, only one except writing. So every node have same responsibility. So every node except write and read. And the decentralization, so there are no one node that know about the detail of other nodes. So every node is peer-to-peer depend, like one node know about the some other nodes, and one node know about the some other nodes. So there are no single point of failure there. Then also workload proportionally for server capacity. As example, a new faster server handle more virtual nodes rather than the old one. So that's the background designs goal, and then move about the a simple the architecture about the Dynamo. So it's using simple API interface, like they store the data with the key and the value as object, and also they use context to track the versioning and handle the inconsistency later. And if we want to get the value, so we just pass the key and we get the values. So that is architecture of the Dynamo. So it's a client request, and so it's going to the server, and server just giving the key. So Dynamo return the value. So if there are any inconsistency, that the application layer will handle that the inconsistency. Yeah, that's for the system architecture. So I will hand over the presentation to the Vidika. Thank you.
Data service. But the big question is, does Dynamo decide which service to store? This is where consistent hashing comes in. Dynamo uses something called hashing. You can imagine it like a circular flow. Both the servers and the data keys are placed around this ring using a hash function called MD5. Now, when a new piece of data comes in, for example, a shopping cart, Dynamo moves clockwise around the ring until it finds the correct server. In this example, key K is stored on node B, but Dynamo does not stop there. So to improve reliability, the same data is copied to multiple servers. Here the data is also stored on C and B. This is called replication, and here the replication power n equals 3. Another important feature is virtual loss. So it, instead of giving one position to each server, the Dynamo has multiple positions. This helps distribute data even. For example, the server can server.
You guys, can you clearly hear? I cannot hear it clearly.
Yes, sir, there are some delay in the voice.
Okay, yeah, just pinning the mask. Let's wait for another 1 minute, right? So then let's see.
Okay.
Can anyone ask her to reconnect or rejoin, or let's try it, right?
Yes, I will ask.
Okay.
Can you hear me now?
Yeah.
Uh, okay. Now, next, let's look at how Dynamo keeps the data highly available using the replication and quorum system. Dynamo uses three important values, N, R, and W. You can think these as three control settings. First, N means the total number of copies or replicates stores for each piece of data. For example, if N equals 3, Dynamo stores the same data in 3 different servers. This improves fault tolerance because even if one server fails, the data still exists elsewhere. Second, R is minimum number of servers need for a successful read operation. The W is the minimum number of servers needed for a successful write operation. Now let's understand this with a simple example. Suppose N equal 3, R equal 2 and W equal 2. This means data is stored in 3 servers. At least 2 servers must respond for read and at least 2 servers must confirm for a write. Dynamo follows an important rule called quorum rule. That means R plus W must be greater than N. Why is this important? Because it generates that at least one server always has the latest update version of the data. So the users are less likely to read old information. Different applications can choose different configurations depending on their needs. For example, a shopping cart system may use balance setting for availability and durability, but product catalog might prioritize faster. Another configuration may prioritize write availability, even if it risks reading slightly outdated data. So dynamic gives developers flexibility to balance the speed, consistency, and availability depending on the application requirements. So next I hand over this presentation to Tagya. Thank you.
Thank you. I'll be covering how Dynamo handles data versioning using vector clocks. So, since Dynamo allows writes across multiple nodes simultaneously, a key question arises: what happens when two nodes have different versions of the same data? So, this is exactly what vector clocks solve. A vector clock is a list of pairs that travels with every version of an object. Every time a node handles a write, it stamps the data with its identity and a counter. So we can track the full history of every piece of data. So let me walk through the example. So you can say the step 1, node SX writes and D1 gets clock, that SX1. So next write D2 to SX2. So in that step 2, two clients update D2 simultaneously through SY and SZ, creating D3 and D4 with no casual relationship. So this is the conflict. So in step 3, on the next read, Dynamo detects both versions and cannot auto-decide. So it returns both to the application. So in step 4, the shopping cart app merges both into D5, nothing is lost. So, here's the reassuring part. In 99.94% of real cases, only one version exists. Conflicts are rare, but when they happen, vector clocks make sure data is never silently lost. So, then let's look at the eventual consistency and conflict resolution part. So, now let's talk about how conflicts are resolved through eventual consistency. Dynamo follows a always writable principle. Writes are never rejected. Conflicts are not resolved at write time, but at read time, and eventually all updates will reach all replicas across the system. So there are three conflict resolution strategies. The first one is application level merge. So they are used by the shopping cart. If Alice adds a book offline and Bob adds shoes from another device, Dynamo returns both versions to the application, which merge them intelligently. Both items are kept, but nothing lost. So second one is last write wins, LWW. So they are used for session management. If you log in from two devices, the most recent timestamp wins. The older session is quietly discarded. So third one is syntactic reconciliation. So there is handled automatically by Dynamo. If vector clocks show one version clearly distinct from another, the old one is garbage collection automatically. So Dynamo uses vector clocks to detect conflict preciously and resolve them through eventual consistency with smart merge strategies. So this is what guarantees the shopping cart is always available and never lose our data, even during failures. Now I invite to Ravisha to continue the presentation. Thank you.
Let's discuss how handles failures. Let's start with the simple truth. In a system without thousands of servers, failures are not exceptions. They are normal. So Dynamo has 4 clever ways to deal with this. Let's discuss one by one. First one is hinted handoff. Image, you order a package, but you are not at home. The courier leaves it with your neighbor with a note saying, This belongs to house number 5. When you come back, your neighbor deliver it to you. That is exactly what Dynamo does. If node A is down during a write, the data is sent to node D instead with a hint that says this is actually belong to A. When node A come back online, node D automatically delivered to E. No data lost. The second one is sloppy quorum. Normally, a strict quorum means you must get the response from a specific node. But if those nodes are down, the whole operation fails. Dynamo is smart. It says use the first and healthy nodes available, not necessarily the perfect ones. Think of a restaurant with 5 chefs. If head chef calls in sick, you don't close the restaurant. The next available chef step in service continuously normally. And the third one is Merkle tree sync. When a node comes back after being offline, why do you know which data missed? You don't want to compare every single record. That would take part. Merkle tree solved this elegantly. Think of it like a book. You first compare the table of contents. If chapter heading match, skip it. Only go to deeper into chapters that are deeper, then down to the pages. You only reread and fix the section that actually changes. This makes sync between nodes fast and efficient. Fourth one is multi-data center replication. Every piece of data is copied across the multiple data centers in different physical locations around the world. So, if the data center is Virginia, lost the power due to hurricanes, the Singapore data center instantly takes over and serve all requests with the zero interruption to the user. Okay. Next, we are going to talk about the membership, gossip, and node management. Sorry, next slide is implementation details. Now look at what actually running inside each Dynamo storage node. There are 3 core software components. Component 1, request coordination. This is built on the event-driven architecture on Java. Every client request get into on state machine that goes through the strategy. The second component is membership and failure detection. This uses something called gossip protocol. Simple analog image and office where every employee once a second walk over the random college and says, hey, here what I know about who present and who absent today. Within a few rounds, everyone in office know the full picture. That is the gossip protocol. Each node contact with random peer every second, sharing membership update. If a server goes quiet, it neighbor notice very quickly. There are also special seed nodes. These are well-known stable nodes that prevent the ring from splitting into isolated groups that don't know about each other. The third component is local persistent engine. Dynamo does pose one specific database engine. It uses pluggable backlink, most commonly MariaDB, but also MySQL or even in memory buffer. Next slide is membership, gossip, and node management. Let's talk about the node join and leave the system and why they never causes downtime. When a new node joins, it gets assigned random position on the hash ring. It then steals the key range from its neighbors, meaning those neighbors transfer their data to the new nodes. Before any transfer begins, other nodes confirm the plan to avoid duplication. It an overly handover. For example, if Node X is in state between node A and node B. Node X take the over responsibility for the keys in those range. Node B, C, and D simply share those range. When a node leaves or failures, the process run in reverse. Because of the virtual node model, the load is spread of evenly across the all remaining nodes. No single nodes become a hotspot or get overhead. How does everyone stay in sync? The gossip protocol. As shown in the diagram, nodes don't broadcast everyone at once. Each node gossips with one randomly selected peer at a time, both directly and indirectly. Over a few rounds, the membership information propages the entire ring. The result, zero downtime. The client library is a partition aware, meaning it routes requests directly to the ring nodes. Its node maintain a consistent view of ring membership, and operators never needs to manually repartition anything. You can add node before the Black Friday and only about of the keys and to move. The rest of the system keep the running without any interruption. Thank you. I will hand over to Tarushi.
Are you speaking, guys? I cannot hear actually. Can you hear?
So,
Can you hear me?
Yes, we can. Yeah. Go ahead.
Okay, sorry. Okay, so we talk about how Dynamo works. Now let's talk about how well it works in real life. Dynamo was tested in one of the hardest possible situations. Amazon's holiday shopping season in December 2006. Millions of people shop at the same time. Here are the results. First number, 99.995% successful response. That means out of the 1 million requests, only 5 failed. Think about that. If 1 million people knock on the door, only 5 people don't get an answer. That's incredible reliable. Other second number is the zero data loss events. Not one single customer lost their data. No missing orders, no missing cards, and nothing. Third number is 5 times faster latency. When write-up buffering was turned on, Dynamo stores write in memory first, then serve to disk later. This made responses 5 times faster during the peak traffic. And the SLA target was 300 milliseconds. That's less than one third of second for 99.9% of the requests. Dynamo hit this goal consistently. One important thing to note: Amazon measures the 99 point percentage, not just average. Why? Because the average hides problem. If 999 people get fast responses, but 1% wait forever, the average looks fine, but the customer is unhappy. Dynamo care about everyone, not just some people. Now let's talk about what Amazon learned from running Dynamo and what problems they discovered. Lesson 1 is client-driven coordination is much faster. Originally, every request went through a load balance, like a traffic officer who tells cars which roads to take, but this added the extra time. They switched to client-driven coordination, where the client already knows which node to talk to directly, no traffic officer needed. The result, read and write speeds improved by the 56% in the 99%. That is the massive improvement just by removing one step. Other one is the right buffering cuts latency, but there is a trade-off. Dynamo can store writes in memory first, then write to disk later. This makes things very fast. But if the server crashes before serving to disk, those writes are lost. So it's like writing notes on sticky notes instead of in a notebook, much faster to write. But if the sticky notes fall off, it's gone. Amazon's solution is make one of the end replicas always do a proper disk write. So you always have at least one safe copy. Lesson 3 is that giving developer control of N, R and W is powerful. Different services need different things. A shopping cart needs to never lose data. A product catalog needs to be a very fast to read. Session management just needs to latest version. By letting developers turn in RW, each team can set up Dynamo for this exact need. It's like a car with adjustable seat, mirrors, and steering. Every driver sets it up for themselves. Now let's talk about limitation. One is routing table doesn't scale to 10 of thousand of nodes. Dynamo uses a full membership model. Every node knows about every other nodes. This works fine for a few hundred nodes. But if you have 10 of thousands nodes, the amount of information each node has to store becomes too large. This is like group chat. If there are 10 people, every can keep up. But if there are 10,000 people sending message every second, it's become unmanageable. Second one is deleted item can come back. This is a tricky one because Dynamo merge version of shopping carts, deleted item can reappear. Imagine you remove product from your shopping cart on your phone, but your laptop is still had an old version with product. When the two versions merge, the product come back. The application itself has to handle this edge case. Dynamo doesn't automatically solve it. So after everything we just covered, consistent hashing, vector clocks, failure handling, performance number, here are the 5 things that truly matter from everything we discussed today. You can choose availability over consistency and it works. Dynamo deliberately choose to be always available even if it is means something showing slightly all data. And this work in production at massive scales and with real customers. Before Dynamo, people thought you always needed strong consistency for serious application. Dynamo proved that's not true. Other one is the Dynamo is proven at Amazon scale. 3 million checkouts in a single day, hundreds of millions of requests, zero data loss. That this isn't a theory; it's a live system that worked. Other one is the combination of technique is what make it special. No, no single idea makes Dynamo work. It's the combination. Consistent hashing, vector clocks, sloping query, market freeze, and gossip protocol. All working together. Each one solve a specific problem. Fourth one is developers should control trade-off. Dynamo exposes the complexity to the developer. Yes, it makes the developer's job slightly harder. But it means each service can be perfectly turned for what it actually needs. And finally, Dynamo changed the industry. Apache Cassandra and React and Amazon own DynamoDB, systems that power application you use every day. So when you open an app, your cart is still there after a network error. There is a good chance system inspired by Dynamo made the possible. Okay, that brings us to end of our presentation on Dynamo Amazon highly available key value. We hope this gave you a clear picture of how Dynamo works, why it is built, and why it still matter today in the world. Thank you so much everyone for listening. Once again, thank you.
Okay, thank you. You guys did a great job, right? So the explanation clearly. And yeah. So let's move to next group, guys.
So, can we start?
Yes, yes.
Uh, Good evening, everyone. We are Group 9. We are going to present about PIC Latin. Before going to explain our presentation, I would like to introduce my team. I am Danojidan and Kobinath, Kajanan, Krishigan, Suiskaran, and Dilakshan. First, I want to clarify why we need PIC Latin as a language. The thing like big companies like Google, Amazon, Yahoo, the employees who working there handle terabytes of data in their daily life. So they need to struggle to handle those type of data. So they need a different language instead of using if they can use traditional language like MySQL like that. But if we take the MySQL, it's too expensive for scale that to the handle those terabytes of data. And if it comes to raw map reduce methods, it's very low level. It's it's not answer for the high level technique. So it's not allow the high level technique. So we can't go on that side also. So in a when we handle terabytes of data, Pigletin is the best way to handle those type of data. Next, we can you can see in the picture, Pigletin come middle of the SQL and MapReduce. I have already mentioned. Um, uh, if you take about the expensive, MySQL is the high expensive. For the performance, it's okay. But if you take MapReduce, it's low expensive, but its performance also it's not allow for the high level operations. Pigletin follow a sequence of steps. For example, if you go for a restaurant, you want a food, you can order the food. I want visa or something. But if you in your home, if you want a food, you need to give the ingredient. In a SQL, we execute a set of query. The system will understand the query. Next, it will think how to execute. Then it will process the output. But in the case of Pigletin, not like that. If we want a set of data, we need to follow the step of first we filter like grouping, something like that. We need to follow a step by step instruction. Next, it's allow the high level operators like filter, group, join, for each. It's allow these types of operations also. And Pigletin is specific for the specific data flows. This follows a specific data flows to handle the executions. I will invite Gopinath to continue our presentation.
Thank you, Tanagidan. Now we need to move the next slide. Um, just can you change the slide, Tanagidan? Yeah, next one. Yeah. Here's the six feature that make bit different from the, I think, from the actual and another field. I think everyone get a good idea from the introduction also. Here's the six features. First one is the data flow language. Quick start to import a fully nested data model. Then UDFS as first class citizens, and parallelism by designs. And last one is the Pigpen Debugger. Which uses a data flow language. Instead of writing one huge SQL query, we write a small step one by one. For example, first we load student data, then filter student older than 18, and finally display only their names. This step-by-step approach makes program easier to read, debug, and maintain. That's the first one. The second one is the fix is very quick to start because no fixed schema is required. We can directly load a raw text file like student.txt without creating a table first. If needed, we can define field while loading, such as name and age. This is the flexibility is useful when handling large amount of raw data. The third one is pick support a fully nested data model. For example, a student record can contain multiple subject marks inside it, like alias having math and science scores together in one record. This structure matches how programmers naturally represent real world data. And the fourth one, pick support user defined function or UDFS. For example, if we want all names in uppercase, we can create a Java function called toUpper and use it directly inside the pick query. This allows developers to extend pick with custom logic. And the fifth one is pick is designed for parallel processing. For example, when grouping employees by department, pick automatically distributes the work across multiple machines. This is make it efficient for handling big data. Finally, Big provides a big PicPen debugger instead of testing with millions of records. PicPen automatically creates a small sample dataset such as alias Pop and the Charlie, so developers can quickly see the result of each processing step and debug easily. Now we move on to the next slide. There's data types. Here's the four data types: atom, tuple, bag, and map. First type is atom, which is just a single value like alias or the number 20. Those are the single value. The Lakers also some single value. The second type is tuple, which is a collection of field. For example, Alice 20-year-old and Colombo together in one row. Those are the tuple values. We can use these tuple values in the Python, I think. The third one is the bag, which is a collection of tuples. For example, a bag contains several students marks like alias with at 85 on board, Bob with at 90. That's a age and name example for the bag. Those are combined of two different one. That's a bag. Duplicate value also allowed there. And the fourth type is map, which stores data as a key values pair. For example, age can point to 20 and a city can point to Colombo. This is a very useful when data structure change frequently. I think now my part is over. I can do this presentation to Kajam.
Thank you, Gopinath. The core operators. The core operators. So now, let's look at the actual commands you write in Piclatin. There are 7 main ones, and each one does exactly one job. First is load. Mm, this is how you bring your data in. You point it at a file, tell it how to read the file, and give names to the columns. That's it. Your data is ready to work with. Next is for each. This applies some processing to every single row in your data. For example, if you want to expand a search query or extract a field, you use for each. It works on one row at a time, which also makes it easy to run in parallel. 10 tiers filter. This is simply keeping the rows you want and throwing away the ones you don't. For example, remove all bot traffic or keep only pages with a high page rank. Group takes all your rows and buckets them by a key. So if you want to group all search queries by user, group does that in one line. Co-group is similar but works across multiple data sets at the same time. So if you have search results in one table and revenue data in another, co-group brings them together by a hierarchy. Keeping each dataset's rows nested separately, we will talk more about this in next slide. Join is the classic database. Sorry, Tanuja, change previous slide. Join is the classic database join. It's actually just a shortcut for co-group followed by the flattening the results and final store. When you done with analysis, store writes the results out to a field. On top of the 7, you also have union, cross, order, and distincts, which work pretty much the same way as SQL. So the core language is just this clean, simple building blocks, each doing one thing, chained together in a sequence. Thank you. Now, Kirsigan, it's your part.
Thank you, Karan. Next slide, Tanuvithan. Yeah. So here we discuss one of the strongest feature of Piclatin, extensibility through user-defined functions. So Pic allow developers to create custom functions mainly using Java and use them almost every course such as filter, for each, group, and join. This gives programmers a lot of flexibility while handling complex data processing tasks. For example, in the script, the top 10 user-defined function is used inside for each statement to generate the top 10 URL for each category. Another important point is that PIC supports non-atomic input and outputs. That means a UDF can work only with symbol values, but also with bags and tuples, which make it powerful for large-scale analysis. The slide also highlight the parallelism is guaranteed on PIC. Only operators that can scale efficiently in distributed system are allowed. Operators like EQ join, grouping, filtering, and projects are supported because they parallelize well in Hadoop. However, pick intentionally execute non-equal joins and correlated subqueries because they are difficult to scale efficiently. So overall, pick balance flexibility and scalability by allowing custom logic while still ensuring reliable parallel executions. So let's move to the next slide. This slide explains how Piclatin scripts are executed internally in Hangoup using MapReduce. The process starts with Piclatin script written by user. First, the phrase and verify check the syntax and correctness of the script. Then pick create a logical plan which represent the sequence of the data operation. After that, the MapReduce compiler convert the logical plan into MapReduce execution plan that Hadoop can run. One important concept here is lazy evaluation. Pick does not execute commands immediately. Instead, it builds NT execution plan first and only start process when store command is reached. This approach allows Pick to optimize the workflow and combine operations efficiently. Another key point is that group and co-group operation usually create MapReduce job boundaries. Operations like filter and forage between them can often be optimized and published into the map of reduce phase. The slide also explains how Pig handles nested bags and large data set. Functions such as count, sum, and average use combines in handoff to improve performance through parallel aggregation. If intermediate data become too large, Pick can spill data to disk using external sorting, preventing memory issues. So in summary, Pick act as high-level layer over handoff, automatically converting user-friendly script into optimized MapReduce jobs. I invite Election to continue our presentation.
Yeah, thank you, Christian. Now we will see the implement part of Cow Bix runs. Compared to MapReduce, there is a 5-step big Latin script and base verifier, logical plan, MR plan compiler, and kernel of execution. There is a 3 categories: lazy and boundary and nested bags. The lazy is build first and run later, and group is one Mr. Job and algebraic UDF spell. The next is debugging, the big pen debugging at the speed of the true. The problem is edit and debugging at DB scale. The single iteration on the database take minutes to hours, scanning roll, sampling, and unreliable join on small sample of reduce empty results scanning in the real bug. The next part will continue by Swiss current.
Thank you, Dilakshan. Now we will move to the slide number 11. That is real usage of Yahoo and what remember. Actually, 3 real use cases via the when the Pick deployed. First one is roll-up aggregate. Roll-up aggregate means counting search term frequencies by day, week, monthly, and geographically. For example, consider in Sri Lanka, how many people in Sri Lanka searched for cricket last week versus this week. So we compare these categories under this roll-up aggregate. And other one is temporal analysis. Temporal analysis means comparing a search query distribution between time period. Time period means consider a month or for likewise. For an example, search patterns between January or February. For consider example for food ordering app in Jaffna district. In a COVID function period, on that time there is no small people order the non-veg and order much plenty of people to veg. Likewise, we can analyze these categorical by temporal analysis. Next one is session analysis. Session analysis means grouping all users, page views, and click together, ordering by a timestamp, then running custom business logic. Fixed nested data model makes sessions a natural data structure. Back event per users, likewise. Mainly, we take from this slide, pick switch between SQL and MapReduce. Best of world. Next, we will move to the main part is our conclusion part. Conclusion part is mainly already Kanoilan said that uh, um, I will move a little introduction, a little summary about this. Mainly, Picletin is between the SQL and MapReduce. SQL is mainly capable for ECVO analyst, but Picletin is ECVO programmers. MapReduce is there is a lot of coding and function and reduce function likewise. So MapReduce is difficult. So the Picletin is in the middle part of SQL and MapReduce. So we need not to have the deep knowledge of related like SQL and MapReduce. SQL is highly dependent in some queries or likewise, but Picletin is not much like that. Next one is Gobinar said they test for data type that are flexible to design, and other one is and Picletin fill in sweet spot more declarative than MapReduce. I already told about it. Then a nested model plus four groups in Picletin, it has more features as in core group. And another one is PicPen dependent. Sandbox dataset let engine debug step by step without touching CB scale product data. Sandbox is an additional feature in the Picletin. And other last one is open source Apache project, fully implemented, run on Hadoop, active browsing user community. Overall, Pic support bags, tuples, and maps likewise. So Pic is a good for data analysts and who handle the big data. Thank you. If you have any questions, you can ask.
Okay, so yeah, good presentation. So yeah, today we talk about the big learning, right? Kind of a not a kind of in-depth like in-depth concepts like this. So it's good to have this kind of stuff. And I think the papers that I shared you, so those are the real implementations where the those kind of technologies are invented, right? So you can have a kind of in-depth knowledge about those kind of tools as well. So yeah, thank you guys. And next week actually we will cover the Apache Kafka, and yeah, you can I will share um, the lecture slides and notes for you. There I think we have right now there are six lectures. Yeah, six lecture slides, and there is another new lecture for next week. It's the deployment patterns, and so then in next week actually we will have four group presentations, and I think we will do lectures around 2 hours, and I think we can cover off our stuff in there. So then so in the 6th of June we will have a kind of I plan to do a kind of a practical session. So then so there is a guest person will join for that one, and right after that one, I think most of the syllabus we covered already. So yeah, let's meet in next week and let's wrap up for today, guys. So I will share the lectures notes. So I'll hand out to your demonstrator, and he will share it. Okay, guys, have a nice weekend.